Well, number one, let's just, is this, yeah, this is taken. Okay, what is this? What's that stand for? And what are those temperatures and pressures? What? 1.00. Oh, 1.00 atmospheres? That's standard pressure.
273 is the temperature.
And standard temperature. Yeah, and we should think about it in Kelvin. Okay, standard temperature is 273 Kelvin. We're talking about gas laws.
The volume is 22.4.
Okay, we're going to get there. So this is STP. So, okay, you're getting ahead. What is the volume, or let's say calculate. Let's use the word calculate. Calculate the volume of 1 mole of an ideal gas at STP. Okay, now what I've said on an ideal gas law problem, if you see 3 of these 4 things, remember these are the 4 variables that affect a gas. If you read a problem and you can see 3 of those 4, and it's asking you to calculate the 4th one, calculate the volume, then you can assume, or you can conclude that this is an ideal gas law problem. I've got all the information I need here to solve the ideal gas law. So this seems this seems like there's not enough information here. Calculate the volume of 1 mole of an ideal gas at STP. But STP is giving you 2 of these things. It's giving you temperature and pressure. So you have temperature, you have pressure, you have N. What you don't have is V. The temperature, and let's use an exact number there, 273.15 Kelvin. It's not centigrade, it's Kelvin. The pressure is 1 atmosphere. The moles is 1 mole. And what is the law? What's the ideal gas law?
Like the R?
What is the...
0.08.
No, what is the ideal gas law? Yeah. PV equals NRT. Talked about wearing that shirt. It has this on it, but it's a short sleeve shirt. Doesn't work today. PV equals NRT. So we've got these laws. Well, I won't write them all right now. Let's stick right here. But when I say what is the law, I mean what is the chemical equation that expresses that law? Pressure times volume equals the moles times the ideal gas law constant times the temperature. PV equals nRT. All right, so we have all this stuff. And what is R again? You got it on your periodic table? Liter atmospheres per mole Kelvin. Yes?
When we're doing temperature, are we always going to have it at 273.15, or is it going to be 273?
All except for this calculation right here, because this is a particular problem I want us to solve. So I want T as accurately as possible. So from now on, 273 is fine. Usually we're dealing with 3 significant figures. You can deal with 273. All right, so since volume is our unknown, we want to isolate volume and get this expression like this. Volume equals nRT RT over P. So we have 1 mole times 0.0821 liter atmospheres per mole Kelvin. Temperature is 273.15 Kelvin. Pressure is 1.00 atmospheres. And to just show how this all works out, the moles here are going to cross out. The atmospheres here are going to cross out. Degrees Kelvin are going to cross out. And the only unit left right here is liters. All right, take out your calculators and do that calculation. Oh, I know the number I wanted to. Okay, that's good. And you get something like what? 22.4? 22.4 liters. Okay, now, here is something you should find a little bit curious. Should be a little curious about that. What gas? What gas are we talking about? What gas is that?
Ideal gas?
Any ideal gas?
Yeah, because that's standard. It's the standard.
Any ideal gas.
It has 1 mole.
So what this is saying is if we had 1 mole, okay, let's put a couple ideal gases down here. Sometimes I need to write on the board because this stuff is kind of neat to see it all at the same time. All right, so we've got this thing right here that volume is 22.4 liters. Our problem here is what is the calculate the volume of an ideal gas at STP. That is the volume of an ideal gas at STP. Helium is an ideal gas. Pretty ideal. Oxygen, nitrogen, hydrogen are fairly ideal in their behavior. Neon, argon are ideal gases. And we're talking about 1 mole of these gases. So a mole of argon is 39.9 grams of argon. A mole of neon is 20.2 grams per mole. Helium, 4 grams per mole. 32 grams per mole. I'm just pointing out here, 28, what is that? 28.02 grams per mole. 2.02 grams per mole. The molar mass is 1.01, but there's 2 of them. This is diatomic. So we're talking about gases, anywhere from 2 grams of the gas to almost 40 grams of the gas is going to have the same exact volume. That's kind of curious, but it is true. It is true. This is the molar mass of an ideal gas at STP. So that's why I put it down here Excuse me, molar mass. It's not the molar mass. It's the molar volume. I'm sorry. 22.4 liters. So this is a problem, and this is the answer to the problem that I want you to remember. 22.4 liters of any ideal gas at standard temperature and pressure is a mole of that gas. That's why on Cytober I asked people to bring in balloons about the size of a basketball. That's about 22.4 liters of gas. So helium balloons with about 22.4 liters of it at the freezing point of water and 1 atmosphere pressure is about a mole of gas. So what this means is you have 6.02 times 10 to the 23rd atoms or molecules bouncing around in that volume. You have the same exact number of gas particles in that volume. And so the big one, the heavy one, is bouncing around more slowly. But it has more momentum. It still generates enough pressure to fill that balloon. You follow me? The little one is bouncing around faster. Less momentum. It hits the sides of the balloons with less force, but they're traveling faster when they do hit the side of the balloon. So they're expanding the balloon. So they're having the same effect, final effect, of pushing the balloon out to 22.4 liters volume. This one's light and moving fast. This one's heavy and moving slowly, but they average out to the same effect. All right, so that's an important problem to do. Molar mass. Let's do another. The ideal gas law problems are the most important ones for us to do. What is the pressure of 4.8 grams of hydrogen with a volume of 20.0 liters and it's at 25 degrees C? All right, let's, here we have, this we have volume. Here we have temperature. Here we have the amount of the gas, but it's in grams. And what is the pressure? So there's pressure, temperature, volume, and an amount of gas. And the pressure is the... So remember, start with the law. All right, I want you to do this problem. I'm going to just give you a few hints. You got to convert the centigrade to what? Kelvin. To Kelvin. Now, you got to convert the 4.8 grams of hydrogen to what? Moles. And you have to rearrange that equation. So what you want is an equation that says P equals what? And go ahead and work on that problem with your hands, with a pencil, with a piece of paper, and with your brain. are we here? It's the 13th. Ali, Andreas?
I'm here.
Chloe?
Here.
Viviana?
Here.
Lucas? Lucas. Mark is here. Michelle?
Here.
Jean? He's here. Natalie?
Here.
Melody?
Here.
Christy?
Here.
Ashley? Amanda?
Here.
Joel?
Here.
Alejandra?
Here.
Daniel? Ashley? Tasneem? KK? Adrian? Oh, Adrian? No. Shantae? Hannah? Where's Hannah? Hannah? T and Egypt.
I mean, if you're, well, come on, I'll do it. I think this is just a trend. This is 6 grams. You can be hydrogen. How many moles is that? How many moles are in 4.8?
All right, I want to give you this kind of a problem because I want you to see that sometimes the amount of the gas can be given to you in grams and not moles. If it's given to you in moles, you can just use it directly. But 4.8 grams of hydrogen times 1 mole of hydrogen per 2.02 grams of hydrogen is going to convert.
Oh, because it's hydrogen too. Two hydrogens.
It's H2.
Gotcha.
The molar mass of hydrogen gas is 2.02 grams per mole.
Because it's two hydrogens.
Remember, I just said the weight of these particles matter. So it's not a hydrogen atom bouncing against the side of the balloon, it's a hydrogen molecule. And it weighs 2.02 grams. 1.01 times 2. So how many moles is that? Too many? Okay. All right, now rearrange this equation. All right, and you get pressure equals nRT over V. And then you can plug these numbers in. What do you get? What do you get? 2.9 what? Yeah. So 2.9. Okay, you're rounding it off. You only got 2 significant figures right there. We're going to add that. We're going to get 3 significant figures right there. 2.91 ATM. Right. That's the right unit. Atmospheres. If you do all this crossing out, you're going to end up with atmospheres left over right here. .91 atmospheres.
Professor,
Yes?
are you going to have the formulas on this next exam?
No.
No?
I'm getting so much help these days. You should see my other class. One guy jumped in and said, "Oh, I'll answer that one." No, we're not gonna. You got to do that. I'm pausing. I'm stalling for time.
Okay.
Because these equations here, you mean?
Well, no, not that. Like the oils and all the other ones.
Yeah, that's what I'm meaning over here.
Oh, yes.
Yeah, that's what I'm referring to. Well, let me pause just for one more minute. So what are these? I want different people to tell me what these laws are. P1 V1 equals P2 V2. So these kinds of problems, the only thing you see in the problem is pressure and volumes. All right, this is a limited problem. This is a limited law, Boyle's law. You can't deal with the amount of the gas or the temperature of the gas. It's saying those aren't changing. If you don't change those, then I can tell you how pressure and volume relate to one another. This one, what's someone else? V1 over T1 equals V2 over T2.
Or V1 T2 equals V2 T1.
This is the same thing. This is another way of expressing that by doing the cross multiplication. V1 times T2 equals V2 times T1. Combined,
T1 over T1 T2. That's what
yeah. Okay, Avogadro. Avogadro relates volume to what?
Moles.
Volume to the moles. Okay, now what I want you to see here, so then we came over, so we got this, that's Boyle. We've got this relationship, that's Charles. And we have volume to moles, that's Avogadro's law. So we took this thing right here and we said, okay, I'm going to multiply this by NT, I'm going to multiply that by NT. And that's how we derived this equation. PV equals nRT. But let's go back to this right here for a second. And let me get something to cover this up. So what law is that? What law is that? What law is that? No, V over N. Avogadro's law. So the ideal gas law is bringing those three laws together, those relationships. Pressure times volume is a constant. Volume divided by temperature is a constant. Volume divided by the number of moles of the gas is a constant. And if we put all those constants together, different constants, we get the ideal gas law constant R. So what I'm saying, we're still getting back to Andres.
Just Andre.
Yes. Andres, question, am I going to give the equations on the exam? I probably will, yes. Okay? But what I want you to appreciate is if you memorize this equation right here, you memorize that equation, and you rearrange it into this, you can see all three of the laws in this right here. This is really the best name for this would be the combined gas law. It combines all the gas laws into one law. So they messed up by combining Boyle and Charles and calling it the combined gas law. This is known as the ideal gas law. That T-shirt, that shirt I have at home was given to me as a present about 5-6 years ago. Some people visited us from Oregon, and the guy asked me what I did, and I told him I teach at Northwest Vista College. He said, "What do you teach?" I said, "Chemistry." I said, "Chemistry?" He said, "The ideal gas law, PV equals nRT." This is what he's telling me. This guy's 45, 50 years old. He said, high school chemistry, he said, that's the only thing I remember from high school chemistry, is the ideal gas law. And about 2 months later, I get an envelope in the mail, and it's this shirt with the ideal gas law embroidered on the shirt. He sent me this shirt, you know, and I never forgot that, because he said, this is, in terms of chemistry, this is the thing that he took away from his chemistry class. The ideal gas law. So now let's use it one more time with a favorite. And Andre, I was asking this question a couple days ago. So let me get a clean slate here. And let's get back to our cylinder of gas. Let's say you're working in a hospital. This thing has a valve on it. It has a cover over it. Screws on there. Let's say this thing is 35.0 liters. It's a tank of oxygen. It's a tank of oxygen, about 35 liters. It's sitting there at about 25 degrees centigrade. It's at 1,500 pounds per square inch. What's happening? It's at 1,500 pounds per square inch. And I'm going to just divide that by 1 atmosphere of is about 15 pounds per square inch. So that's about 100 atmospheres pressure. 100 atmospheres. So I mean, that's what we got. We got a cylinder of gas that's 100 times the pressure of the atmosphere sitting in the tank. And the question is, what weight of oxygen is in this tank? Yeah. Yeah, very good. So what weight of oxygen is in the tank? So the unknown really is moles. Find N, and then you're going to need to convert the N to grams. You got it? Let's see what your N is. Where's your N?
Right there.
That's N?
Mm-hmm.
No, so N is moles.
Oh, okay, moles, yeah.
That's moles. And now you have to convert moles to grams.
Okay.
Okay, remember now, N is going to come out in moles. The units of N are going to be moles. And you have to convert the moles to grams. This is what I'm trying to have you see now in these ideal gas law problems. The amount of gas could be asked for in moles or grams, but the law itself gives you moles. So whenever it's asking for a mass of the gas, you've got to go from the moles and convert it back to grams. So let's get that far. What is N? How many moles of oxygen will it be?
How many moles?
4,576 grams.
No, how many moles of oxygen? 143 moles. And then you're going to need to multiply this. Remember, oxygen is O2, so it's 32 grams per mole. So you're converting your moles to grams, and Daniel, how many grams is it?
4,576 grams per mole.
1,576? 4,576 grams of oxygen, or maybe 4,580. You could round that off to 4,580 grams of oxygen. Okay? So, I mean, what that's telling you right now, you take that oxygen tank, they bring it in, they put it in the hospital, they strap it to the wall. It weighs a certain amount. They use it, the tank's empty, it's lighter. It's lighter by 4,580 grams. That's a lot of grams. It's 221, what is it, how many grams per pound? It's, you could figure out how many pounds that is, but the tank will actually be lighter when they take it out of the hospital, take it back to get it refilled with oxygen. It feels heavy. The tank itself is pretty heavy. It's a pretty thick steel tank. But they have these tanks in the hospital. We have tanks, we have a tank of nitrogen in the lab over here. Same sort of deal. It's at about 1,500 pounds per square inch, or about 100 atmospheres pressure. All right. Any problems I didn't do here, I'm going to just leave them to you. The combined gas law problems are the hardest ones. I'll tell you what I will try to do. Now, this isn't a promise. This is this is something I'll try to do. I'll try to sit down and work these problems out and then reload them into Canvas as the answers to this answer sheet. So if you have some time to kind of do this and you're kind of wondering, I wonder if I got the right answer, I'll work them out and get them there. Or Joel will work them out and he'll give them to me and I'll post them. All right? I'll look them over. Something like that. Now, let's see where we are on our slides. Where are we on our slides? Here is this calculation we did. I kept that at, well, that's fine, 0.08206. We rounded off to 0.0821. That's fine. But we did that calculation. We got that molar volume. I might even have that. Who had their periodic table out here? Do I have the molar volume on there? Yeah, it even has the molar volume. Volume of a gas of 1 mole of an ideal gas at STP, 22.4 liters. Okay, there's, I tell you what I want to do. We got a half an hour. I'm going to whisk down through solids or liquids and solids and just point out hydrogen bonding. And then I want to, so I'll try to do that by 9 o'clock. And at 9 o'clock, I want to explain molarity, which is actually going into the next module on solutions. But I want to at least introduce molarity to you. So I'm going to bounce through these slides pretty quickly here. Let's just see what they are. There's a bunch more problems here, converting different pressures. This is 14.7 pounds per square inch equals 1 atmosphere. You kind of, so if you had to convert PSI into atmospheres, you need that. PSI equals pounds per square inch. That's what PSI. So when you fill up your tires to 32 PSI, it's 32 pounds per square inch. It's about 2 atmospheres. All right? 15 pounds per square inch is roughly an atmosphere. 32 pounds per square inch, 2 atmospheres. Any of you have those cars with 60 pound per square inch tires on them?
Just remind you to go up to 40.
40? Yeah, there are some tires, aren't there, that they get them up to 60 pounds per square inch.
That's the donuts.
Those donuts. Yeah, they're very high pressure tires.
Yeah.
I mean, in the Army, we had it up to 90.
To go over a certain speed with them.
Is that right?
Yeah.
Okay.
Like,
See,
heat up and then it'll expand it even more. Yeah, it'll just pop.
I was gonna say in the Army, ours was up to.
what's the advantage of those tires?
That's well, I don't know, but yeah, I don't know why they wouldn't make like. I think it's just
They have
because
those now.
It's smaller.
So you can
It's smaller
drive
in the
with them.
vehicle, you know. and
Oh, the
it's
donut, the little donut.
Yeah,
Okay.
instead of like a air, and
Okay.
matches the pressure of the other tire.
But ordinarily, you're filling your tires to about. I went in another country. I went into a gas station. There was an air pump there, and they had it in bars, which is atmospheres. So it's 1, 2, 3 bars.
Did you do your conversion?
4 bars. Yeah, to do the conversion. 'Cause, I mean, if I had filled my tires up to 32 bars, it would have blown them right off the car. And it was just wham! There goes my tire. You know, there would have been 32 atmospheres.
Good thing you're a chemist.
Yeah. Well, the guy in front of me was saying, oh, 4, 6 bars, and I'm saying, honey, we're getting out of here. This guy's tires are going to blow. So we got to get out of here. All right. So there we go. So now, this chapter also wanted to deal with liquids and solids very quickly. You can look at that. There's a bunch of information here you can come back to. Talking about liquids, we talk about viscosity. Where do you come in contact with that? Honey. You take a jar of honey off the shelf, and it's a viscous liquid. Viscosity has to do with flow. How does that liquid flow? Water is a low viscosity liquid. It flows very easily. Honey, maple syrup, the oil, automobile oil, and 10W40 automobile oil is talking about its viscosity. What is the viscosity blend of that motor oil? Viscosity, the flow characteristics. Surface tension. Water is a high surface tension liquid. You go diving into water, you can belly smack on the water. It hurts. While you're breaking through the surface tension of the water, one thing soap does a couple things, but one thing that soap does to water is it lowers its surface tension so that it will wet things. You wax your car and the water beads up on the car. The water is not really wetting the car. You put soap in that water and it'll wet the car. It'll come out evenly on the car instead of being beads like this on the car. It beads up because actually the water is attracted to itself, and it's forming a little bead. One other characteristic of that, you notice how when you take a pitcher of water and you pour it, and the water follows itself down. It doesn't just spray out all over the place. It comes down in a little stream of water. Why? It is actually attracted to itself, and it stays as this stream of water. That's because of its surface tension and its attraction to itself. Vapor pressure. Liquids do have a vapor pressure even below their boiling point. Water boils at 100 degrees C, but a cup of water sitting out on your countertop for a couple days will disappear, right? It will evaporate. Why? Because it has a certain vapor pressure even below its boiling point. Water molecules are escaping out of the cup slowly but surely, and then eventually it evaporates. Vapor pressure. Okay, just some terms, you know, evaporation, a liquid converting into a gas, condensation, a gas converting back into a liquid, vapor pressure, the pressure exerted by a vapor, by a liquid. So normal boiling point is at 1 atmosphere. So when we say what the boiling point of water is, we're saying it boils at 100 degrees centigrade at 1 atmosphere. What's the implications of that? In Denver, Colorado, water boils at a lower temperature. You say, well, it's still water. Yeah, it's still water, but it's not at 1 atmosphere. It's at less. It's 1 mile high in Denver, so there's less atmospheric pressure above it. Pressure's lower. The water gets up to that pressure at a lower temperature. So water's boiling in Denver at maybe 97, 96 degrees centigrade. That's why it takes an egg longer to boil in Denver, longer to cook. That's why you will see recipes that'll say at high altitudes, you know, cook this for another 20 minutes, 10 minutes. Why? The boiling point of water is lower there. To boil your spaghetti, you got to cook the spaghetti longer in Denver. It's cooking at a lower temperature. Okay, intermolecular forces. Don't worry too much about these, and this is where Newton might do a deep dive into some of this. I don't know.
Yeah.
Does it? Van der Waals and London forces.
Yeah.
It's talking about, these are minor, these are intermolecular, between molecules. That's what we're talking about here. Between. So you need to understand inter and intra. In high school, you had intramurals, right? One class playing another class in the school. Intramurals is one school playing another school. Schools playing between them, all right? So between, within. So we're talking about forces occurring between molecules. So here's the one I want you to know about, is hydrogen bonding. This is an important intermolecular attraction or force to take into consideration. And I think we have gone over this before many times. Water, the water molecule. You got a hydrogen on an oxygen. This has an electronegativity of 3.5. This has an electronegativity of 2.1. The difference in electronegativities, or what we called delta E, is 3.5 minus 2.1 is 1.4. That's a big difference. And so we called this a polar covalent bond. Polar covalent bond. We're saying that the attraction of the electrons, there are two electrons in this bond, And the electrons are preferentially being attracted to the oxygen, and electrons are negative. And so what we leave out here is a proton all by itself, and it's positively charged. These electrons are there sometimes, so we say it's a partial positive charge here, a partial negative charge there, but the bond has a polar nature to it. It has a negative end, a positive end. So now, let's take two water molecules. Yes.
So if they're never equal, then that means it has like a dipole moment, right? Or no?
Yeah. This would have a dipole moment.
When they're different.
And the bigger that electronegativity difference, the bigger that dipole moment is. All right? So even methane, you've got carbons and hydrogens, but they don't have a very big difference. So they have a very small dipole moment to them. Very little separation of charge. That's why methane and gasoline is a non-polar molecules. But water is polar. So this positive is being attracted to that negative. This negative is attracted to this positive. So I'm going to put these dotted lines here. And this is what I'm calling a hydrogen bond. All right? I don't draw a line. This is a covalent bond. It's a polar covalent bond, but it's a covalent bond. It's two electrons shared between the hydrogen and the oxygen. That is an intramolecular thing going on there. That's a bond. They're attached to each other. I mean, if you, I got a great example here. Okay. Velcro. All right? This thing is attached to this. This is attached to that. Now, hydrogen bonding is kind of like that. We've got this attraction now between these two strips, but I can't, it takes a lot of force for me to break that, but it doesn't take that much force for me to take the Velcro off of the Velcro. So that's what I'm talking about here. This is a strong bond. That hydrogen is bonded to that oxygen in that molecule. But this molecule has an attraction to another water molecule here. It isn't this strong of an attraction. If I heat this up, I can break those bonds and that water molecule will go into the atmosphere. Follow me? A little bit of energy, put it on the stove, heat it up. It doesn't destroy the molecule. The molecule goes into the atmosphere. H2O molecules. That's what humidity is. It's H2O molecules floating around in the air. But they have overcome that hydrogen bonding there, that force of attraction that they have in the liquid state, and bam, they've gone off into the atmosphere. This is happening. This is what's happening right at the surface. If I were to imagine this right here, you got this last little hydrogen bond right here. You got this molecule getting ready to evaporate, and all it needs is to just overcome that attraction right there, and off goes the molecule into the atmosphere. That's what's happening. Those molecules that have enough energy to do that, and you get evaporation, slowly but surely. And then you have all these other molecules down in here attracted to one another in the liquid state, if I were to heat this up, put a Bunsen burner under there and heat that up, all of a sudden, more and more of the molecules have enough energy to overcome that, and they evaporate. They're starting to boil and evaporate out. That's hydrogen bonding. All right, now where does hydrogen bonding come up? Why do we make such a big deal out of it? It is actually, you've heard DNA is a double helix, right? It's a double helix. What holds those two strands of DNA together? Hydrogen bonding. Hydrogen bonding holds them together. They are two distinct strands, molecular strands. They get wrapped together, and it's hydrogens attracted to oxygens or nitrogens or whatever it is that is forming hydrogen bonds. That is an important attraction, but not as strong. So you can break those hydrogen bonds like you open up a zipper. This is exactly what DNA is doing. There's a protein that comes down and unzips it, breaks those hydrogen bonds so it can open up and replicate and zip back up again. So that's hydrogen bonding. Whenever you have a hydrogen on an atom that has fairly high electronegativity, so fluorine has a high electronegativity, nitrogen, sulfur. Remember, electronegativity is high in this corner right here. So whenever you have, an ammonia molecule, ammonia, you can get another ammonia molecule right here, and you end up with hydrogen bonding. The hydrogen to the nitrogen, the high electronegativity molecule, and the nitrogen to the hydrogen on another one. So it's intermolecular. And I think that's enough of that. Okay, molarity. Any questions about that? That's hydrogen bonding. So whenever you have a hydrogen on an oxygen, a nitrogen, a fluorine, or a sulfur, you can get hydrogen bonding. It's just showing it. What's the effect of that? Well, what this is saying right here is these molecules do not have any hydrogen bonding. You're starting to get hydrogen bonding here. It's really raising the boiling point. Here's hydrofluoric, the gas, hydrogen fluoride, and here's water. That hydrogen bonding is what makes water have such a high boiling point. You eliminate that hydrogen bonding, and that would be a gas at room temperature, and well below room temperature. Okay, the solid state, probably the most I need to say about is right here. Here are 4 examples of solids, different kinds of solids. Here is a covalent solid, and the example is diamonds. A diamond is carbon. You say it's just, isn't coal carbon? Yeah, coal is carbon, but it's not bounded together the way diamonds are. You got a carbon bound to 4 other carbons covalently. Very, very strong. An ionic solid, sodium chloride. We've talked about that. Sodium and chloride ions in a crystalline pattern. Molecular solids, if you took methane, the natural gas that's heating your home today, if you cooled that down really cold, it would freeze as molecules, methane. And then here's a molecular solid. Here's an example of a molecular, or a metallic solid. You have aluminum nuclei, the nucleus of aluminum atoms in a certain array, and you have a sea of electrons around it. This is why metallic solids conduct electricity. You put a potential on either side of this aluminum here, and the electrons will move in that direction like water moves in a pipe. All right, it's enough of that. So, the next unit is number 9, or module 9, has to do with solutions, and an important concept we get to in 9 is concentration. And maybe, what is today? Tuesday. Thursday. So maybe Thursday I'll try to bring in some, try to remember to bring in just some water and some solids and do a little dissolving in them. But concentration, just imagine for a minute if I had a glass of water up here, 2 glasses of water, and in one of them I put a teaspoon of salt in there. And you say, you could taste it, it's salty. But in the other one I put 2 teaspoons of salt in there. They're both salty, right? But one of them has more salt in it than the other one. So we could start talking about what is the concentration of salt in the one glass of water versus the other glass of water. What is their concentration? And we will talk about concentration in 2 terms. We'll talk about molarity, and we will also talk about a weight volume percent, or what some books now are calling a mass volume percent. This is the chemical laboratory preferred concentration, molarity, capital M. This is what you will find in hospitals. Saline solution is 0.9% saline. All right, saline solution is just not any concentration of saline. It's 0.9% saline. And why is it that number? That is the concentration of salt in your bloodstream. So when you go to the hospital and get an IV, and they will always start saline first. Start a saline IV. They're just opening up a pathway to administer a drug. They don't put water in your veins. They put saline solution in your veins at this concentration, because that equals the concentration of the bloodstream. Concentration of salts, and there's various different salts. So we'll get to weight volume percent eventually, but let me just introduce molarity. You can kind of see the word mole in there, right? Are you surprised? I mean, once we introduce mole, we just keep harping on it. So what is molarity? It's the moles of solute per liter of solution. Moles of solute per liter of solution. So what is a solute? What is a solution? A solute is what is dissolved in the water. Well, I'm talking aqueous solutions right now. We could talk about all different kinds of solutions, but usually we are talking about things dissolved in water. So what is it that's dissolved in water? In the glasses of water with salt in them, the salt is the solute, and the volume of liquid in that glass is the solution. I'm not talking about just the volume of water. I'm talking about what is the volume of the solution. So moles of solute per liter of solution. So if I wanted to make a 1 molar sodium chloride solution, that would mean I would have one mole of sodium chloride in 1 liter of the solution. Tell me how much I have in there. That's would be 1 molar. So when you see this here, you should think moles per liter. Capital M, really the units of molarity are moles per liter. Moles per liter. Moles of solute per liter of solution. And this one right here, in order to make that solution, I would need a mole of sodium chloride. Sodium is 22.99 grams per mole. Chlorine is 35.45 grams per mole. So sodium chloride is 14, one up there, 13, 14. 58.44 grams per mole. So if I had 58.44 grams of sodium chloride and I put it in a liter container and filled that liter container up with water, I would have that many grams per liter of solution, and that would be a 1 molar NaCl. I don't think I'll push this any further than this, but it isn't enough to put a label like this on a bottle, because I could have 20 bottles of things there that are all at 1 molar. You got to tell me what is it? It's 1 molar sodium chloride. It could be 1 molar hydrochloric acid. It could be 1 molar nitric acid, etc., etc., etc. Okay, we were talking about this a little bit before class even began, so if some of you came in before you heard this, the quizzes, the 5 quizzes for the Module 8 on gases have been extended to Friday at midnight. Some of you got in there and did them. A couple of you were having trouble accessing them. I think people were accessing them different ways. So some people found the path to them and some people didn't. So I've extended them to Friday. And then we'll talk a little bit more on Thursday about Module 9. Those aren't due until the 19th. When is the 19th? What day is that? Is that Monday night?
Sunday? Yeah, Monday.
Monday. Okay. So Module 9 is coming due on Monday. We'll see. We'll talk more about it on Thursday. Okay? But make sure you get those quizzes done by Friday.